Let's begin with something that's truly foundational in chemistry: the size of atoms. Imagine holding a copper wire in your hand or watching chlorine bubble out during an experiment. Ever wondered why copper is so malleable and chlorine so reactive? Well, the answer lies partly in the atomic radius. Atomic radius is the distance between the nucleus of an atom and its outermost electron shell. But since electrons don't orbit in neat circles and their clouds are fuzzy, we estimate the size using bonded atoms. For example, the bond length in chlorine molecule Cl2 is 198 picometers. So, its covalent radius is about 99 picometers, that's half the bond length. Now, as we move from left to right in a period, like from lithium to fluorine, atomic radius shrinks. Why? Because the nuclear charge increases and pulls the electrons closer without adding extra shells. But when we move down a group, from lithium to cesium, atomic radius expands because new shells are added. The same logic applies to ionic radii, but here's the twist: when atoms lose electrons to form cations, they shrink. Sodium atom has a radius of 186 picometers, but sodium ion is just 95 picometers. Anions, on the other hand, like fluoride, expand. Fluorine's atomic radius is 64 picometers, but fluoride ion jumps to 136 picometers due to electron-electron repulsion. Fascinating how losing or gaining just one electron reshapes an entire atom's size, isn't it? Have you ever tried pulling a balloon away from a wall after rubbing it on your hair? It resists, just like an atom resists losing its electrons. That resistance is measured as ionization enthalpy, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. For instance, if we take sodium in the gaseous state, removing 1 electron gives a sodium ion and a free electron. That's written as Na gas gives Na plus gas plus E minus. This process requires energy, always. The first ionization enthalpy is usually less than the second because once the atom becomes a positive ion, it holds on to its remaining electrons more tightly. Across a period, ionization enthalpy increases. Why? As we go from left to right, nuclear charge grows and atomic radius shrinks, making it harder to remove electrons. But down a group, it decreases. Elements like cesium can lose electrons easily due to their large size and increased shielding. You'll notice exceptions too, like boron having lower ionization enthalpy than beryllium. That's because boron loses a 2p electron, which is more weakly held compared to the 2s electron in beryllium. Even oxygen shows lower ionization enthalpy than nitrogen due to increased electron repulsion in its half-filled p orbital. These nuances help us predict reactivity across the table. Think of fluorine. Just 1 electron away from achieving noble gas configuration. Naturally, it pulls in electrons with incredible zeal. The energy change when an atom gains an electron to form an anion is called electron gain enthalpy. For most elements, it's a negative value, meaning energy is released. For example, chlorine gas gains 1 electron to form chloride ion, written as Cl gas plus E minus gives Cl minus gas. This reaction releases energy. In fact, chlorine has one of the most negative electron gain enthalpies, around minus 349 kilojoules per mole, even more than fluorine in practice, because fluorine is so small that adding an electron causes significant repulsion. As we move across a period from left to right, the electron gain enthalpy becomes more negative due to stronger nuclear pull. But down a group, it becomes less negative because the electrons are added farther from the nucleus. Take oxygen and sulfur. Sulfur's larger size means less repulsion, so it has a more negative electron gain enthalpy than oxygen. Real-world relevance. These trends explain why halogens form strong acids like hydrochloric acid and why metals generally don't like gaining electrons. Now let's shift gears and talk about something very practical: bonding. When atoms form bonds, they don't always share electrons equally. The atom that pulls more strongly on shared electrons is said to be more electronegative. Electronegativity is a relative measure and not directly measurable like ionization energy, but on the Pauling scale, fluorine tops the chart with a value of 4.0. As we move across a period, electronegativity increases due to stronger nuclear pull and smaller atomic size. Down a group, it decreases because atoms get larger and their pull on shared electrons weakens. For example, lithium has an electronegativity of 1.0, while fluorine has 4.0. These differences determine bond types: ionic, polar covalent, or nonpolar. Want a real-life example? In water, the oxygen atom is more electronegative than hydrogen, which is why water is a polar molecule. And remember this, high electronegativity correlates with non-metallic behavior. So as we move from metals to nonmetals across the table, we are really watching electronegativity take charge. Let's look at how elements behave when they bond. Valency is a classic concept, the number of electrons an atom tends to gain, lose, or share to achieve a stable configuration. For representative elements, valency is usually the same as the number of outermost electrons or 8 minus that number. For instance, oxygen with 6 valence electrons tends to gain 2, valency is 2. Sodium has 1 electron in its outermost shell, it loses it easily, so valency is 1. Now, in modern terms, we often talk about oxidation states, a more formal way of describing electron distribution in compounds. Let's compare two examples. In O2, or oxygen difluoride, fluorine is more electronegative and takes on an oxidation state of -1. Since there are two fluorines, oxygen must be +2. In sodium oxide, NaOH, sodium is +1 and oxygen is -2. This idea of oxidation state helps chemists write correct formulas and understand redox reactions. So when you're balancing equations or predicting product formation, valency and oxidation states are your best friends. Now we come to one of the most exciting applications: reactivity. Why do sodium and chlorine react explosively, forming common salt? The answer lies in periodic trends. On the left side of a period, elements like sodium have low ionization enthalpies and lose electrons easily. On the right, halogens like chlorine have high electron affinity and readily gain electrons. This creates a strong drive to react. In the middle of the table, say with elements like aluminum or silicon, reactivity is moderate. Down a group, reactivity increases for metals like potassium and rubidium because outer electrons are easier to lose. For nonmetals like fluorine and iodine, reactivity decreases because added electrons face less nuclear pull. We also see this reflected in oxide behavior. Sodium oxide reacts with water to give sodium hydroxide, written as NaOH plus H2O gives to NaOH, a basic solution. Chlorine heptoxide reacts with water to form perchloric acid, Cl2O7 plus H2O gives to HClO4. And right in the middle, oxides like aluminum oxide are amphoteric, reacting with both acids and bases. This spectrum of reactivity is chemistry's way of expressing balance: basic on the left, acidic on the right, and versatile in the middle. So let's quickly wrap up what we've explored today. Atomic and ionic radii tell us how size changes across the table, shrinking across a period and expanding down a group. Ionization enthalpy reflects how tightly atoms hold onto their electrons, higher across a period, lower down a group. electron gain enthalpy shows how readily atoms grab electrons, more negative for nonmetals, less so for metals. Electronegativity ties it all together, giving us a sense of bonding behavior, increasing from left to right and decreasing top to bottom. We looked at how valency and oxidation states help us predict compound formulas and how reactivity patterns explain the behavior of acids, bases, and amphoteric oxides. Periodicity isn't just theory, it's a predictive map of the chemical universe, explaining why sodium fizzes in water, why chlorine disinfects pools, and why noble gases just sit there inert. I hope this session helped you see how the periodic table is more than rows and columns. It's a living, breathing logic chart of chemical behavior. Stay curious, and I'll see you in the next class with more molecular marvels and atomic adventures.